Ever wondered how your computer talks to servers on the other side of the planet? How does your email instantly reach someone thousands of miles away? Or how you can stream a video without it turning into a garbled mess? Pauses for effect. The answer lies in network protocols, the digital language that makes all digital communication possible. In today's video, we're going to demystify these protocols, explain how they work together to create the modern internet, and even show you some practical examples of how you can work with them. Stay tuned because this knowledge is essential for anyone who uses the internet, which means pretty much everyone these days. So what exactly are network protocols? At their simplest, network protocols are standardized sets of rules that dictate how data is formatted, transmitted, and received across networks. Think of them like diplomatic protocols that allow representatives from different countries to communicate effectively, even if they come from completely different cultures and speak different native languages. These rules ensure that devices can understand each other regardless of their underlying hardware or software differences. Without protocols, the internet as we know it would simply cease to exist. Protocols handle everything from addressing, how devices are identified on the network, to error checking, ensuring data arrives intact, and security, protecting data from prying eyes. To understand how different protocols work together, we need to talk about one of the most important conceptual frameworks in networking, the OSI model. OSI stands for Open Systems Interconnection, and it provides a structured framework for understanding how network communication should work by dividing the process into 7 distinct layers. Table showing OSI model layers, layer number, layer name, function examples. Application interface for user applications HTTP, FTP, SMTP. Presentation data translation, encryption SSL, TLS. Session manages connections between apps NetBIOS, RPC. Transport end-to-end connections, reliability TCP, UDP. Network logical addressing and routing IP, ICMP. Data link physical addressing, error detection Ethernet, PPP. Physical raw bit transmission over physical medium cable, fiber optics. Each layer has a specific function and communicates with the layers above and below it. This modular approach means that protocols can be developed for specific layers without having to redesign the entire network stack. For example, the physical layer worries about transmitting raw bits over cables or wireless signals, while the application layer deals with high-level protocols like HTTP that your web browser uses. While the OSI model is great for learning, the real-world implementation used by the Internet is the TCP/IP model. This simpler model has just 4 layers that roughly correspond to the OSI model. 1. Application layer, combines OSI application, presentation, and session layers. 2. Transport layer, same as OSI transport layer. 3. Internet layer, same as OSI network layer. 4. Link layer, combines OSI data link and physical layers. The TCP/IP model is the actual framework that powers the modern Internet. The name comes from its 2 most important protocols, Transmission Control Protocol, TCP, and Internet Protocol, IP. Let's look at some of the key protocols in this model. Starting at the top, we have the application layer protocols. These are the ones that interact directly with user applications. HTTP/HTTPS, Hypertext Transfer Protocol, is the foundation of web browsing. When you visit a website, your browser uses HTTP to request and receive web pages from a server. HTTPS is the secure version that encrypts data using SSL/TLS to protect your sensitive information. DNS, the domain name system, is often called the Internet's phone book. It translates human-friendly domain names like youtube.com into machine-readable IP addresses like 142.251.32.110. Without DNS, we'd have to memorize numbers for every website we want to visit. FTP, File Transfer Protocol, is designed for transferring files between computers. It's especially useful for uploading files to web servers. Though older, it's still widely used, with secure versions like SFTP addressing its security limitations. SMTP, Simple Mail Transfer Protocol, handles the sending of emails. When you hit send on an email, SMTP is what gets it from your device to your email provider's servers and then to the recipient. Moving down the stack, we come to the transport layer, which is where we find two critical protocols. TCP, Transmission Control Protocol, is connection-oriented, meaning it establishes a stable connection between devices before transmitting data. It breaks data into packets, numbers them, and reassembles them in order at the destination. If packets are lost or damaged, TCP retransmits them. This makes TCP reliable but slightly slower. UDP, User Datagram Protocol, is connectionless. It simply sends packets without establishing a connection or checking if they arrived. This makes it faster but less reliable. UDP is perfect for real-time applications like video streaming or online gaming where speed is more important than perfect delivery. At the Internet layer, we have IP. Internet Protocol is responsible for addressing and routing data packets. Every device connected to the Internet has a unique IP address that functions like a mailing address for data delivery. IP determines the best path for packets to travel from source to destination. ICMP, Internet Control Message Protocol, is used for error reporting and diagnostic functions. The popular ping command uses ICMP to check connectivity between devices. Let's see some of these protocols in action. First, let's open a command prompt and use nslookup to see DNS at work, nslookup youtube.com. See how it resolves youtube.com to an IP address. That's DNS doing its job. Now let's look at how we can use the ping command, which uses ICMP. Ping google.com. This sends ICMP echo request packets to Google's servers and measures how long it takes to get a response. Great for testing connectivity. Real-world applications. Let's connect this to your daily internet use. When you browse a website, multiple protocols work together. 1. DNS resolves the domain name to an IP address. 2. TCP establishes a connection between your browser and the server. 3. HTTP/S requests and delivers the web page content. 4. TLS/SSL encrypts the communication if using HTTPS. When you send an email. 1. SMTP sends your message to your email provider's server. 2. The message is routed across multiple servers using SMTP. 3. POP3 or IMAP allows the recipient to retrieve the message. When you stream video. 1. UDP is often used for the video data itself for faster transmission. 2. TCP might handle the control commands and metadata. 3. HTTP/S may deliver the web interface. So there you have it, network protocols are the unsung heroes of the digital age, working behind the scenes to make all our digital communication possible. From the physical cables carrying raw bits to the application-level protocols that bring us rich web experiences, these standardized rules ensure that our increasingly connected world can, well, stay connected. If you found this explanation helpful, do us a favor and hit that like button and subscribe for more content about how technology works. We love helping demystify the complex systems that power our modern world. Now we'd love to hear from you. What networking topic should we break down next? Routing? Firewalls? Cloud networking? Let us know in the comments below. And if you have questions about anything we covered today, drop those in the comments too, we read every single one. Thanks for watching, and remember, in a world full of digital noise, understanding how things work is your superpower. See you in the next video.